Good day, everyone. I'm Aminu Munir. I'm the one to take. Good day, everyone. I'm Aminu Munir. I'm the one to take this real analysis tool. So, in this real analysis tool, all one is about the real analysis tool is the limit of the function. That is, we're having a function and we're having the limit of that function. And then the continuity of a function. That is, a function to be continuous in some interval. And we're having what is be continuous at a point. Then we're having differentiability. We're going to talk about all this differentiability. Then integrability. So also talk about the integrability. The first thing is just start with the limit of a function. That is, before we just come to a continuity and differentiability and integrability. So don't confuse with this limit of a function and the limit of a sequence, of a convergent sequence. So there's a difference between the limit of a convergent sequence and the limit of a function here. So the limit of the function, so here we're going to talk first about the limit of a function. So now define what is a function. What is a function? A function is a relation, that is a relation between two non-empty sets, say A and B. That is, we're having a set, suppose we're having a set A and we're having a set B. So that is a relation between this set is non-empty, then we're having as element A, B, C, D. Here 1, 2, 3, 4 continuously, or just let it like that. So a function is a relation between two non-empty sets A and B, say. Such that this means such that for each element in A, that is for each element here, we pick element from A, is mapped to a unique element of B. That is, this is mapped to a unique element. Unique means it mapped to a single one element of B. That is, you cannot have this function, this A, from the function to map into this one and map into this B. So this one we say is mapping to a unique, so we will not map to a 2. So therefore, if it is mapped, if A map to 1, then that's all. That is the image. So we can now say the image of 1 is the image of A is 1. That is, from this function, f is defined for f of A is equal to 1. F of A means the image of A from A is equal to 1 in B. So therefore, this is the function we are talking about. So this function that is taking this element from here, mapping into this element, so it has a limit. So therefore, so we say this function is said to be a one-to-one, that is, if no element left on map, it's a one-to-one. If we're having this one map to this one, and suppose this map to this map to this, and this map to this. So this is a one-to-one mapping, because we are clearly seeing, or this is a one-to-one. We are clearly seeing has an image, B is an image, C is an image, D is also an image, and this one. So every element here is already mapped. So therefore, this mapping, this function is a one-to-one mapping. That is, every element is mapped onto. So the onto, if f of s is equal to f of y, then f must be equal to y. So we are saying onto mapping. For this mapping to be onto, it must have the image of, if the image we're having, the image of A is 1, the image of B is 2, and the image of C is 2, then this B must be equal to C. We cannot have those two elements cannot map to one element. Likewise, one element cannot have two images, like this one. Two element is a mapping to one. So this is not an onto mapping. So and here this one is having two images. So this also not an onto mapping. If this is happening, we are saying this B must be equal to this C before this mapping to be an onto mapping. So and here we're having this one D is having two images. So therefore this must be equal to a 3 before the mapping to be an onto. An onto means no element that has two images and no element that will map to two images. So we define, suppose we're having C and we're having D. So we're having 1, 2, 3, and we're having, let's say x1, x2, x3. So this will map to this one, Definitely, this one will have to this, this one will have to this, so we're having a function. And this clearly, this function is a one-to-one because no element left on map. It is on to each one mapped to a single element. So this is a meaning of one-to-one. And if we're having the image of x is equal to the image of y, we imply x must be equal to y. That is, if the image of x, these are x, and the image of this one is the same, their image is 2. So therefore, then they must be equal. And if we have if x is not equal to y, implying the image is cannot be the same. So that is a function, a one, this an onto function. So therefore now the limit of the function, this function has a limit. So therefore the limit of this function, so by definition, so we define the limit of the function, let f be a mapping. So this is a mapping from the domain where we are just taking a value into R. So suppose a mapping from A to B. So if this is a mapping from A to B, so therefore by this definition is saying a mapping f from the domain E to R. Now, not B now, where R is the set of the real number. So a mapping, let F be a mapping from E to R, be a function with domain E and with domain E, and suppose, so with domain E, so I mean, and suppose that X naught is an accumulation point of E. And the N is what is an accumulation point? So given a domain, suppose a domain, this E is defined to be equal to, let's say minus 1, 0, 1, 2, 3. If this is a domain, then what is the accumulation point of this domain? An accumulation point of the domain is the point that has is a point that has a that there is a sequence that converges to that point. That is, there is a convergent sequence that the limit that point is the limit of a convergent sequence. Then we say that point is an accumulation point. Suppose given a sequence xn to be equal to n over n plus 1. And so therefore taking the limit as n tends to infinity of Sn is equal to the limit of this, definitely we are going to get the limit as n tends to infinity of n over n plus 1, which is equal to 1. So therefore in this case, since there is a sequence that converting into 1, how do we get the limit of a sequence? Either we just divide here by dividing by the answer, here divided by n, here divided by n, here divided by n. Then we just push our n to be infinity. So here should be 0. So that we can have 1 over 1, which is equal to 1. So therefore, in this case, there is this sequence that combined into this point. Then therefore, 1 in this domain is an accumulation point. So therefore, 1 is an accumulation point. The accumulation point is a point where there exists a sequence that converges to that point. So therefore, we say suppose that x1 is an accumulation point of E. Then we write the limit as n tends to x naught, that is at x is going to x naught of the function f of x is equal to f. If for every epsilon greater than 0, there exists delta greater than 0. So what is this epsilon? Epsilon is a number between 0 and 1. So if you all those numbers, not only one, all of them, all those numbers between 0 and 1 is epsilon. There exists delta greater than 0. Delta is also number between 0 and 1. So that the absolute value of f of x minus L is less than epsilon. That is, you having the absolute value of the function f minus the limit of that function, this f, is less than epsilon. The distance between the function and the limit is less than 0. Whenever 0 less than the absolute value of x minus x naught is less than delta. Why 0 is less than this is showing that x is not equal to x naught. That is, this x and x naught, they are not the same. That's why we say 0 is less than them. If it is 0, this implies they are equal. So therefore, x is not equal to x naught, but x is trying to attain x naught. It's converging to their going. So therefore, this is the graph of the function now and the limit of the function. So here we're having this is f of x, the function of x in this axis, and here is x step in this axis. So and here we're having a function, a point x naught, and here we're having what f of x naught, which is equal to what L. That is, as x tend to x naught, that is x will be x naught. So I mean f of x naught should be equal to L. So therefore f of x will be equal to L in this graph. Then from here we're having x naught, then they will meet at this one. So therefore, I mean, this is the point where the function f of x naught is meet with what? With x. And here, when we just remove a small number, we say this delta is number between 0 and 1. So therefore, this x, when we just remove something from it, then we can get the result from here. And this will definitely not be what? The limit, this L, when we just remove epsilon from it. So therefore, we have to change this. And here, when we just add something, this x naught, we just add a small number with it, then we can have the result from here. And this limit, when we add something, a small number between 0 and 1, we can have it from here. And so therefore, they will definitely attend to this one. So this graph, we obtain it from this one. From the absolute value of f of x minus the limit L is less than epsilon, whenever this is less than whenever absolute value of 0 less than absolute value of x minus x naught is less than delta. And so therefore, from here we have, from this absolute value we obtain this. How? So having from here absolute value of f of x minus the limit L is less than epsilon. So from here we can now say minus epsilon. So minus epsilon is less than or equal to what? F of x minus L, which is less than epsilon. So that is negative of this, then we just remove the absolute value of less than or equal to. Then we just add this one to this one. So therefore, adding L throughout here will be L minus epsilon, which is less than or equal to f of x, which is less than or equal to epsilon plus L. So I have it like this. So therefore, this implying f of x is between this interval, that is f of x is inside this interval L minus epsilon, comma epsilon plus L. So that's why from here we're having L minus epsilon and L plus epsilon. F of x, which is equal to L, is between this interval. That is, this function is between here. That is as x tends to x naught. So definitely this x will be what? Going to x naught. So therefore, f of x is the same thing as f of x naught. And from here we're having from here we're having 0 less than absolute value of x minus x naught, which is less than delta. So in this case, we have a minus delta is less than or equal to x minus x naught. When we just remove the absolute value, which is less than or equal to delta. So from here, I'll just add x. We have just add x naught to both sides. So this implying we have been adding x naught in this side. We have been x naught minus delta, which is less than or equal to x, which is less than or equal to delta plus x naught, or x naught plus delta. So this implying x is between this interval. That is, x is between the interval x naught minus delta from x naught plus delta. So having x is between this interval. That's why having x naught is between this interval. Remember, we say x is approaches x naught. So therefore, definitely this x is going to, we can use x naught as what? As x. So therefore, it's between this interval. X naught, when we just remove, you can clearly see this x is going to remove. When we just remove something from it, that is, we're having this point x, we're removing something from x, we can have the result here. And adding something to x, we can have the result here. Likewise, from here, we're having L, then we remove something from L, we go below the L. And adding something to this L, we go just go above. So therefore, here, so this is all about this. So you can have delta to be equal to delta epsilon. It's the same thing. We are saying this delta is a number that depends on epsilon. And epsilon is a number between 0 and 1. So delta equal to delta epsilon. This implies we can say this delta is the same thing. It's depending on epsilon. So therefore, the example is given. Prove that the limit as x tends to pi of 10x minus 11 is equal to 39. So we have to show using this delta epsilon delta definition. So we say now solution. So therefore, we need to show the limit as x tends to 5 of 10x minus 11 is equal to 39. So you can clearly, when you test, when you take 5 here, you can get 5 into 10, you get 50. 50 minus 11 is the same thing as 39. So we are asked to show, not to substitute that this one to be this. So I have to show using this definition. Using this definition, for this one to satisfy that one, it needs to satisfy, for this one to be true using this definition, it must have to satisfy this definition. So satisfy this, so therefore, from here we need to show that we need to apply the definition. That is, if for every epsilon, or can I say if for all epsilon greater than 0, there exists a delta greater than 0 such that, so I can write my surname like this. It is something it is something as we're having this such that means so that, and for every or for all in the same thing, then there exists. So I can write there exists like this. So therefore, so that what the absolute value of f of x minus, so therefore our function now is this. This is our f of x. Absolute value of 10x minus 11, then we have been them minus 39 is less, whenever this one is less than epsilon, then therefore hence the result we have finished. So therefore we can have this absolute value of s minus l is less than this epsilon whenever this happens. So therefore we can now see the absolute value of f of x, absolute value of f of x minus 5 minus the limit l, sorry, 39 is less than epsilon whenever 0 is less than the absolute value of x minus 5, which is less than delta. So this implying absolute value of f of x minus 39, which is our l. So f of x is 10x minus 11, then we get minus 39. We need this one to be, once this is less than epsilon, then therefore the result is proof already. So therefore this is equal to, so get absolute value of 10x minus 11 minus 39, and this will give us minus 50, and we can just factor the common. We can factor the common out. The common here is 10. So this is equal to absolute value of 10 into x minus 5. When we remove here, we get 5. Then we have this. So remember, the absolute value of AB is equal to absolute value of A, absolute value of B. You can just split this one without any, this inequality without any changes. So therefore, this is equal to, you can remove this is 10, absolute value of 10, absolute value of x minus 5, which is the absolute value of 10 is 10. So therefore is 10, then absolute value of x minus 5, and this one is less than delta from here. I can say this is less than, I can remove this one and put delta. And so therefore this is less than 10, then we have this is delta. And from here, it's less than delta, which is equal to epsilon. So therefore, where or we can now say delta is equal to epsilon over 10. So we can divide both sides by this, so that we can get our delta to be epsilon over 10. So this implying, the absolute value for every epsilon greater than 0. So we have absolute value of 10x minus 11 into 10x minus 11 minus 39 is less than, from here, 10 delta, which is equal to, our delta is epsilon over 10, which is equal to 10 into epsilon over 10. So therefore this is cancelling this, which is equal to epsilon. So we can now say whenever whenever absolute value of this one is true, whenever 0 is less than the absolute value of x minus 5, which is less than delta. This will be proof. Then the next example, the second one is example 2. Example 2 is saying show that the limit as x tends to 3 of x squared is equal to 9. So we need to show that this limit as x tends to 3 of this is equal to 9. So we can clearly see that when we just substitute this x to be 3, so we can have 9, 3 squared is 9, which is equal to 9. So we are not asked to substitute this one together. So we need to prove this one using this definition, delta epsilon definition. So therefore we can now say solution. So now we need to show that the limit as x tends to 3 of x squared is equal to 9. So therefore this is happening if for every epsilon greater than 0 there exists a delta greater than 0 such that, so we have been the absolute value of f of x minus 9 is less than epsilon. So this is happening whenever absolute value of x minus 3 is less than delta. That is, our x naught now is 3. Therefore, comparing with this one, we have x minus x naught. That is, as x tends to so x minus x naught is less than delta. So here we are having x tends to 3. So here we are having x minus 3 is less than delta. And here we are having the absolute limit as x tends to x naught f of s is equal to f. So having this absolute value of this function minus f. Here, so therefore it's less than epsilon. And so here, therefore, we are having the limit as x tends to 3 of x squared is equal to 9. So here we have the absolute value of f of x, which is equal to x squared, then minus the limit 9 is less than epsilon. Whenever this is satisfied, then hence I will already prove the result. So from here, absolute value of f of x minus 9 is equal to absolute value of f of x is x squared plus 9. X squared plus 9. X squared minus 9. We are having x squared minus 9. And here using difference of 2 squared. So therefore this is equal to, we can write this one as absolute value of this x squared minus 9. We can write it as x minus 3 into x plus 3. So we can write this one. And by splitting the absolute value, we say the absolute value of AB is equal to absolute value of A, absolute value of B. So we can split this one into 2. So using this one. Therefore, this is equal to the absolute value of x minus 3, then the absolute value of x plus 3. So we have this one. And from here, we get the x minus 3 is less than delta. So we can write this is less than, so I can substitute this one. Instead of here, I can have delta absolute value of x plus 3. I have this one, absolute value of x plus 3. So therefore, I will go and look for the value of this x and come back and substitute here. And so therefore, from here, so we can say absolute value of x is equal to, and so from here we have this can be written as less than delta into, so it's less or equal to, when we just split the absolute value from here, it's less or equal to absolute value of x plus absolute value of 3, which is 3. So from here, looking for the value of this absolute value of x in terms of our delta. So in terms of delta, we means this x minus 3 plus 3. So we can remove 3 and just add 3, special 0. So this x can be equal to x minus 3 then plus 3. So if our delta, if this less than delta is minus 4 here, so we can write x in terms of delta. We already just look at this one is here. So write the same thing then add the same so that we can have the same thing here. So therefore, by triangular inequality, um, this is less than or equal to absolute value of x minus 3 plus absolute value of 3, and this is less than, and this is less than delta from there. So I can now say let delta to be equal, let delta to be less than 1. I think delta to be less than 1, number to be 1. So therefore, putting this one, so this is less than delta. And so therefore I can now say this is strictly less than, this is delta, that is 1 plus what? Plus 3. So this is equal to 4. So from here it's implying the absolute value of x is less than, is less than 4. So therefore I can just, and now I've got my value of x, then I can come back and substitute into here. So I can write, I can name this is equation 1. So therefore, then the equation 1 become less than or equal to delta into absolute value of x plus 3, and this is less than delta into absolute value of x is 4, so we get 4 plus yes, value 4 plus 3, which is equal to 7 delta. And we can say this is equal to excellent. This is equal to excellent, implying delta is equal to, then make delta something here, epsilon over 7. So now we have delta to be equal to epsilon over 7 and delta to be equal to 1. So we choose delta. We can now say for every epsilon greater than 0, we can now choose delta to be equal to the maximum, delta to be the minimum of delta 1, which is 1, and delta 2 epsilon over 7. So we are always used to take delta that is having epsilon, because this delta is simply on delta epsilon, is depending on epsilon. So now choose delta to be equal to epsilon over 7. So this implies the absolute value of x squared minus 9 is less than or equal to, from here is less than or equal to 7 delta, which is equal to 7, our delta is epsilon over 7, so I mean epsilon over 7, 7 will cancel 7, which is equal to epsilon. So this is happening whenever absolute value of x minus 3 is less than delta. So this is just about the limit of a function. So I'm going to stop here. Inshallah, next week we will continue. So if you like this video, you can subscribe. So just start the limit of a function. We're going to, there's a one-sided limit, that is limit from the right is and the limit from the left. And they will say the limit of a function is said to be exist if the limit from the right is equal to the limit from the left. So I'm going to talk about that next week. Inshallah, you can subscribe to this video to our YouTube channel.